award ceremony is right in the corner. So next page. We have already organized a few webinars. So those projects are the finalist projects. So the first is the presented last month, the Zhengzhou link. One click, please. And the second webinar is about the Dong'an Lake Stadium. Also, it's from China. Next. And the third one is Jianghe Hui landscape pedestrian bridge. Next, please. And all those webinars are associated with e-learning. So in e-learning, you can find all kinds of electronic-based information there. And please explore it. You won't be disappointed. Next page. Well, in here, you can find the webinars previously conducted, including the webinars we organized last month. And also for today's webinar, you can also find information there. Next one. Okay, today we have the Mr. Xiaofei Wang, and he's a senior engineer at China Railway, and he got his master degree from Central South University, and he have designed quite a few famous projects and published papers and patents. So I think I'll pass the microphone to Mr. Xiaowei Wang for the presentation. All right.
Okay.
Hello. Hi, Mr. Wang. So it's all yours.
Okay. Good evening, respect professors, distinguished colleagues, and dear friends. First of all, I would like to extend my sincere gratitude to the EPSI for organizing this conference and providing us with such a valuable platform to share and discuss our academic achievements. It's a great pleasure to meet so many industry leaders and experts who are deeply committed to bridge engineering. I'm truly both honored and excited to be here today. My name is Wang Xiaofei from China Railway Siyuan Survey and Design Group Company Limited. Today I'm privileged to present my team's research titled Innovation Design of Demolition Construction Collaborative Technology in the Zhengzhou Rainbow Bridge. It focuses on a practice of bridge reconstruction over large railway marshalling station. We address the critical challenges of safety and efficiency through innovation, demolition, construction, integration. Let's dive into the details. Part one.
All right.
The research background and project overview. The city Zhengzhou is a major transportation hub in central China. It's not only rich in history, but also a city of dynamic development. It is crucially located at the intersection of Beijing to Guangzhou and Lanzhou to Lianyungang railways, a nexus dominated by the Asia's largest marshalling station, the Zhengzhou North Marshalling Station. Since its commissioning in 1963, This station has acted as the heart of China railway network. Against the backdrop of China's rapid urbanization, old municipal bridges like the one in our case faced two key pressures: outdated functions and poor compatibility with infrastructures upgrades. This challenge is particularly acute for bridges over busy railway marshalling yard, where any demolition and reconstruction must avoid disrupting railway operations while also meeting growing traffic demands. The Rainbow Bridge in Zhengzhou is typically example. It spans across the largest Zhengzhou North Marshalling Station, crossing 17 tracks from west to east, with numerous control points and extremely limited construction space. The task presented unique engineering challenges. The original arch bridge was built in 1994 with spans of 122 plus 62 plus 62 plus 122 meters and 4 lanes in two directions. However, with the accelerated urbanization of Zhengzhou, the original bridge's functional deficiencies become apparent. First, traffic capacity shortage. 4 lanes fail to cope with the heavy flow on Zhengzhou's North Third Ring Road. Second, the inconvenient connections to surrounding roads, including the Beijing to Guangzhou Expressway, significantly hampered traffic efficiency. Third, the clearance under the bridge became insufficient for the expansion at Zhengzhou North Marshalling Station. To solve these problems, we designed a new bridge with 3 key upgrades. First, structure: 3-span continuous single rib steel box arch with spans 121 plus 125 plus 121 meters. Second, the function: 8 lanes in 2 directions and 60 kilometers per hour design speed, significantly improve traffic capacity and meets future renovations requirements for the railway station yard beneath it. Third, landscape: retained original rainbow style with dynamic shape, become a new urban landmark. The project started in May 2021. Original bridge demolished in June 2022, and the new bridge was completed and open to traffic in September 2023. The part 2, safe demolition of original arch bridge. The original bridge crossed 30 tracks from west to east. The first span crossed 13 tracks. The two 62 meters middle spans had no tracks beneath them, and the fourth spans crossed 4 tracks. And the existing underpass roads on the north and south sides of the original bridge had very heavy traffic, ensuring the safety of opening trains as well as vehicles and the pedestrians using the roads on both sides was considered a priority during the demolition. Given the bridge complex location and limited working space, an innovation overall construction plan was devised with a focus on ensuring the operational safety of the railways beneath the bridge. The plan involves several steps to move the bridge out of the railway safety range before disassembly. Move the two 62-meter spans of steel truss arc laterally to the bridge demolition platform on the north side for disassembly. Move the 122-meter spans of steel truss arcs on the east and west side across the railway track longitudinally to the location of the middle two spans, and move them laterally to the bridge demolition platform for disassembly. Before construction, erect a protective shed over the railways to ensure their operational safety, and erect protective sheds over the underpass roads to safeguard vehicles, traffic, and pedestrians. Pedestrian safety. Based on the stress characteristics of steel truss arcs, featuring a working type incremental launching device with jacking slide blocks. A multi-support design reduces the stress on the truss members to a rational level during the incremental launching, maintaining the safety and reliability of the original bridge. This method ensures the operational safety on the railway and shortened the overall construction period. Part 3. The single-ribbed continuous girder arc composite structure and is the new bridge. As a landmark of Zhengzhou, the Rainbow Bridge embodies the deep emotions of citizens and has witnessed changes in urban development. To accommodate the planning and upgrading of the railway station yard beneath the bridge, our project team considered various factors including location, traffic flow, and spatial layout. We proposed a 3-span continuous single-ribbed steel box arch bridge, designed with spans of 121 plus 125 plus 121 meters, retaining the multiple arcs of the original bridge, resulting in a single-ribbed 3-arc configuration of small arc plus large arc plus small arc. An innovation single-ribbed continuous girder arc composite structure system is adopted for the bridge. The placement of the single arc rib at the center of the bridge deck optimized the spatial layout, enhances visibility for drivers, and allow construction and maintenance of arc ribs in the middle of the deck. This design also effectively reduces the impact of the bridge on the railway. The main arc features an unequal height arc rib and inverted trapezoid steel box sections. with variable widths and heights. The middle arc is 36 meters high, with a rise span ratio of 3.47, while the side arcs are 20 meters high, with a rise span ratio of 6.05. The arc rib transitions gradually from a narrow and high cross-section at the bottom to a wide and flat cross-section at the top. This unequal height designs take into account the structural load-bearing capacity and landscape effect. The girder is a multi-box wise variable steel box girder structure. The bridge deck is 38 meters wide in the standard section and 55.8 meters at the interchange ramp, connected to Beijing to Guangzhou Expressway. To enhance traffic functionality and optimize spatial use, the two 62 meters small spans in the middle of the original bridge are combined into a single span, eliminating the middle piers. The design frees up space beneath the bridge and provides sufficient margin for future expansion. Also, we designed an advanced health monitoring system and intelligent patrol robots utilizing the artificial intelligence technology to replace manual inspections. A robot comprises a track system, supports a climbing drive, and a mechanical arm system. It can automatically and intelligently inspect the interior of the steel box arc, enabling smart detection and facilitating visual management and maintenance within the constrained space of the arc rib. This innovation reduces long-term operation and maintenance costs. To make the robot work well in such complex and constrained space, we have 4 case innovations. The first one is lightweight prefabricated 3D track. It lets the robot carry loads, climbing slopes, and turn, so it can adapt to the different complex roads. The second is a flexible walking mechanism, which helps the robot pass smoothly through horizontal and vertical curves. It has strong anti-overturning ability and come with self-locking and anti-sliding functions. These 2 innovations get ideas from the running system of light rail. While light rail travels around the city, our robot travel between city connecting bridges, achieve a similar effect. The third new feature is the independently developed 4-axis mechanism arm. It can get closer to key structure inspection points in narrow spaces and automatically adjust camera settings based on the shooting distance to get the best image quality. The fourth new feature is the post-processing platform. It has multiple intelligent defect detection techniques to local defect and solve them visually. At the same time, it uses computer vision and natural network techniques to match defects, and
Shall I cannot hear you. Do you have like internet problem? Xiaofei, can you hear me? Hi, Brenda, can you hear Xiaofei? Or just my problem? Okay, okay, I'll call him. Better now? Hi, Xiaofei. I think Xiaofei got an internet problem. I think I'll call him to rejoin the Zoom and try to Hi, sorry everyone. I just talked to Xiaofei. He got the internet problem and he will um, rejoin the meeting and continue from where it was broken. Let's hold for like up to 1 minute.
OK 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 OK。
Okay, I think Xiaofei's back. Hello, Xiaofei, can you hear me? Hello, hello, Xiaofei, can you hear me? All right, I think the internet, the Wi-Fi internet is restricted in some places, but the technology is not. So let's wait patiently for Xiaofei.
Can you hear me?
Xiaofei, I still cannot hear you. Hello?
嗯，哎，
Oh,
夏老师，
okay.
那方便我用您的
可以了，可以了。
手机在
Yeah.
那边。
No, 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 we can hear you now. No, it's all good now. Please continue from these slides. Yes.
哎，夏老师，喂，夏老师，我直接说是吧？好嘞。I'm sorry. The the part for demolition construction collaborative technology. The biggest challenge was coordination, demolition, and new construction over a busy marshalling station. The traditional method separated these two phases, leading to a long construction period and repeatedly safety risks. Our solution is demolition construction integration by transforming the demolition system into a construction platform. Follow the 6 case stages. Stage 1, lateral movement and disassembly of the original bridge, just like the picture 1. Stage 2, longitudinal incremental launching of the original bridge. Stage 3, transform the demolition platform into a new bridge assembly platform by adjusting elevation and position. Stage 4, longitudinal incremental launching of the new bridge girders. Stage 5, in situ erections of new bridge arch bricks. And Stage 6, complete suspender installation and system conversion. In this project, the original bridge movement system was innovatively transformed to realize the integration of demolition and construction. During the demolition process, the pier foundations of the new main bridge were constructed simultaneously, and the steel box girders were prefabricated in advance. By raising the transformed demolition system, rapid positioning and incremental launching were achieved, which optimized the construction and installation procedures and reduced complex process during construction. It only took 16 months from the completion of the old bridge demolition to the opening of the new bridge to traffic, which was 40% shorter than the conventional construction period. Meanwhile, the consumption of steel structure for temporary measures was reduced by about 500 tons. Part 5, conclusion. This project established a new bridge type specifically for crossing large railway marshalling stations, with multiple advantages such as rational stress distributions, a straightforward bridge deck layout, enhanced driving visibility, a streamlined bridge shape, and convenient connection conditions at the approach bridges. The bridge type demonstrates superior terrains, adaptability, and landscape harmony compared to conventional eco-span layouts, offering a new technical model for the construction of municipal landscape bridge and bridge with special crossing conditions. Second, the Zhengzhou Rainbow Bridge represents the first instance in China of bridge construction that cross a marshalling station through in situ assembly of large girders segments and longitudinal movement using the transformed bridge demolition system. This innovation solution facilitates the rapid construction of long-span arch bridge over existing railways, significantly reducing construction and operational risks for similar projects while delivering substantial social benefits. And third, the construction of the bridge is highly significant for enhancing the structure of Zhengzhou Expressway network, removing the current traffic bottlenecks ensuring the railway operational safety and improving the overall life quality in Zhengzhou. Upon completion, the new bridge preserved the historical memory and reflect the spirits of the time. It significantly relieves the east-west traffic pressures on the North Third Ring Road, further accelerating Zhengzhou's development as a national central city and making a substantial contribution to the city's rapid growth. That's all. The Zhengzhou Rainbow Bridge project shows cases how innovation can address the safety efficiency problems in complex bridge reconstruction over busy railways. We hope our experience can provide insights for peers working on similar projects worldwide. That's all. Thank you.
All right. Thank you, Mr. Xiaofei Wang, for your nice presentation and also good try to solve the internet problems. So for the audience, any of you have questions, you can type it on the screen, and I can transfer the questions to Mr. Xiaofei Wang. So allow me to raise questions first. So your presentation, Xiaofei, your presentation is not complicated, but the technology, the project itself is very complicated and interesting. So the Zhengzhou Rainbow Bridge project was transformed from the demolition system into a construction platform. This is quite interesting. So what is the key technical considerations when you consider both the old bridges and the new bridges together?
Um, uh, Thank you for your question. Ensuring the transformed systems compatibility on two core technical methods. First, we decide the support system to accommodate both the old and new bridge. For the old bridge's truss structure, we added supports at key joints based on its stress characteristics, ensuring stabilities when the old bridge moves laterally and longitudinally out of the railway safety range. Meanwhile, we fully considered the support system's adaptability to the new bridge's steel box structure. For example, arrange supports at the new bridge's main girders, diaphragms, and webs. Additionally, we developed a working type incremental latching device with the jacking sliding blocks, which kept the stress of the old bridge truss at the regional level and the new bridge stress at the regional level. We also reversed prefabricated structural interface on the device and demolition platform that meet the new bridge's assembly requirements, laying the foundation for the conversion of the demolition system into a constructed platform. Second, we integrated precise spatial controls with elevation control. Before converting the demolition platform into a construction platform, we conduct rigorous surveys and calculations to adjust the platform's elevation and position, ensure they fully matched the new bridge's assembly requirements. For elevation adjustments, we installed steel pie columns with flange connections between the original platform supports and the new working elevation. The flange connection enabled fast, precise, and reliable elevating lifting. We chose this method for its high reliability and efficiency, which avoid the time-consuming processes of the traditional welding or on-site reconstruction. These methods
Hello again, cannot hear you. Hello. Hi, sorry audience. I think Xiaofei was disconnected again, but he will rejoin. I think we have one or two more questions. So let's have one more try. Well, recently we have like more and more bridge demolition projects. I think not only in China but also worldwide, and also the city updates. We have all this kind of projects. So this technology should be um, very interesting to all of us. And this is very typical. And it's not only like destroy the bridge, but also transfer from the demolition system to a construction platform. This is very interesting. There are a lot of details inside, but in the presentation, I think we cannot go that deep. But still, the technology is there. So, and in the future, if we have like similar projects that if we get good feedback from the audience, I think we can add up more uh, seminar, similar seminar or webinar uh, in the YAPC platform. All right, Mr. Xiaofei Wang is back. Hello. So, yeah, I think we have one more question from the audience. No, two more questions. One is from Wasim. Sorry if I pronounce wrong. Is there any challenge in seismic design for these forms of bridges? So, is there any seismic consideration during the construction process? Hello? Well, maybe I can answer the question a little bit uh, because the Zhengzhou city basically in the middle of China, so it's not usually the seismic effect is not that important. So, and this is not a new a design for a new bridge. So I guess the seismic effect is not considered. So all right, because of the bad connection, I think uh, I shall thank all the audience and end the seminar. All right, thank you very much. That's so much for today. You have a good one. Bye.